All right, so we're back. Sorry about the interruption. I've got some technical difficulties going on here. Let's go back to where we ended. We were talking about uh, step number 3, which is to compute the t-statistic. T-statistic is just going to come from beta j hat and the standard error of beta j. I'm not going to make you calculate these for multiple linear regression. So you're just going to get these from regression results. So you just make sure you know where to find these in your regression table. So once we have made this calculation, what we can do is we can go over to our drawing that we made, and we can kind of plop down. I'm going to change this. We can plop down where at whatever this value is. So let's say it's right here. So this is our t-statistic. We'll just call it t-stat for short. So if it's right here, that means it's within this rejection region, this colored region. So if this was the case, then on our next step, draw a conclusion, we could say, well, that's in the rejection region. It's far enough away from 0 to where we can say, we're willing to accept being wrong because we're far enough away. That's some good evidence. So we would reject the null hypothesis. However, let's say it wasn't in the rejection region. So let's take a look at this right tail test. And let's say our t-stat was right here. Okay, so that is not within the rejection region, meaning it's not far enough away from 0 for us to be comfortable saying we have evidence that it's different than 0. So in this case, we would say we fail to reject the null hypothesis. Okay. So moving on, let's chat about dummy variables real quick. So dummy variables, if we remember, they're just these binary variables. They take on a value of 0 or 1. When they're by themselves, they represent intercept shifts. Okay, so we'll take a look at that here. So for example, if we have a dummy variable that is female, then we wanted to see what the effect is of education on wages, and we included female in our regression. So maybe we had something that looked like this. So we could have wages are equal to they use alpha notation here for the coefficients. That's fine. And they use delta for the dummy coefficient. So we can just follow their notation here, but a lot of times I'll just use betas. So we could have alpha 1 times education plus alpha 2 times female. Okay, so what is if we ran this, then what we could do is we could say, well, let's put ourselves, if we wanted to see what this regression line would look like for a female population or male population, well, remember what we talked about as far as omitting a variable. We're not including one for a variable for male, right? So we've omitted that. So that means male is our base category. So if we're looking at just males, that means that this female characteristic, this is going to be 0. Okay, so our equation then would be alpha 0 plus alpha 1 times education. Okay, so that would be this line right here. Okay, but if we wanted to know what this regression would look like for females, well, first of all, let's assume that the coefficient is going to be negative, which they use delta 0 here. I forgot to change that, but that's what this means is the coefficient on female is going to be negative, meaning that females often get paid less for the same amount of work, same amount of education and qualifications. So we would expect that if we were looking at this equation for females, that it would be lower than that of males because this is going to be negative. Okay, so we look at this graph and we see that's what we see. Okay, so this one is where we're looking at females. Okay, so this coefficient here has shifted down our regression line. Okay, so that's in general what we can think about as a dummy variable, at least when they're on their own. As I mentioned before, we could have some variables that are categorical. They could be more than just binary, so 0 and 1. So one of the main ones that we talked about for that are the car types. So we could have Toyota, Ford, Chevy. Okay. If we wanted to work with these within a data set, we'd have to kind of convert these into dummy variables. Stata is really good about that. We can put a I dot before anything that's categorical, and it will automatically generate these variables, and we don't actually have to make one and keep it in our data set. And dirty up our data set with those, since all the information we need is actually contained within that. So why would we want to pollute our data set? But you have to keep in mind that just like if we had gender, and assuming that everyone in the data set identified as either male or female, then we would only have either of those things, and we have to omit one of them. So in this particular case, we would have to omit Toyota, Ford, or Chevy, right? We couldn't have all three of them, because that would mean our MLR3 is going to be violated. For more details on that, make sure you go back to see the prior video when I discuss that. Okay, and now let's chat about nonlinear relationships and interactions. So we may have some sort of a relationship that actually looks like this. Okay, so if we took the natural log of both sides, then it would look like this. This looks like something that's doable as far as linear regression goes. Okay, so there may be some sort of nonlinearity that we want to take care of. And remember, when we're talking about nonlinearities, as far as using OLS to predict, to find some sort of a regression for, we're still linear in our parameters. Okay, so this ln b0, this is just a constant. Okay, it's a natural log of some number beta 0, but it's one number. It's just a constant. So that's good. This beta 1 right here, that's just a number. Okay, so there's nothing different about doing this than doing our other things as far as our interpretations go. Or excuse me, not as our interpretations are different, but as far as our ability to do them and satisfy MLR2. So I would advise you to keep this table handy. Okay, so remember, this one comes straight from the Wooldridge book, but remember, when we are using logs, then our interpretations are going to change. Okay, so the level, that's the one that we use most of the time. So we've got a dependent variable y, we've got an independent variable x, and our interpretation is of this beta 1 is just a change in x times beta 1 is equal to the change in y. Okay, but once we start adding logs, we have to kind of start thinking about percentages. So, for example, in the log-log model, we've got the log of y and the log of x for our dependent and independent variables, and we would say, well, a 1% change in x is represented by a beta 1% change in y. Okay, now let's think about interactions. Okay, so interactions are another type of nonlinear thing that we might see show up. So, for example, again, if we're looking at wages and education, and whether or not you're female, so this is kind of what we saw before, but now we add in children. Okay, now you might consider that women might have a different effect of having children than men. So what we can kind of do with that is we can interact the effect of being female with the effect of having children. So this beta 4 is representing this interaction between these two. Okay, and notice that I included both of the bits of the interaction. Generally, that's something you want to do. Okay, we'll go over the marginal effects for that if you remember we need to do that. So we'll go over that in just a bit. But I wanted to bring up polynomials real quick because it's actually very similar to interactions. So polynomials, as you might expect, are just when we have some sort of polynomial in our regression. So we might see something like wage equal to beta 0 plus beta 1x plus beta 2, maybe x squared, and maybe so on. And a quick note about this because this is actually in the news a good bit these days about at least as far as econometric type news, that if you're trying to fit a lot of models with a lot of polynomials, you got to be careful that you're not overfitting because they're going to fit your local data really well, but as far as like predicting something else, it's going to be really awful for that. So for example, in the project, and you're looking at COVID data, for example. So that's why it's in the news a lot, as people are using polynomials to kind of predict where we're going. But that's a bad idea to use a lot of polynomials because you're going to really fit the local data really well. But if you're fitting that local data too well, you might actually be not leaving it very open to future movement. And so, that's actually can be a bit of a problem. That's not going to be on the test or anything. Since that's just since it's been something people have been discussing a lot lately, I figured I should bring that up. For this particular example, we could use, if we had this. We have this, looks like we've got some exponential action going on here. So if we wanted to do a regression for that, we could do wage equals beta 0 plus beta 1 education plus beta 2 education squared. What's another way to write that? We could just say education squared is education times education. And that looks a lot like the interactions we were just doing. And it turns out we can do calculation for the effect of education, the marginal effect for education in a similar way to what we did for interaction. So let's see, how do we do that? Let's say we've got this model, wage equals beta 0 plus beta 1 education plus beta 2 female plus beta 3 children plus beta 4 female times children. Okay. So what we want to do when we write out this theoretical model to get this marginal effect is we want to just take the derivative with respect to whichever variable we're trying to find the marginal effect for. In this case, we're interested in finding what is the effect of being female. Okay, so if we do that, we're going to take the derivative of each bit. We're allowed to do that. We can, when we're doing a derivative, we can take a derivative of each term. So what's the derivative of beta 0 with respect to female? It's nothing. There's no female term here. Same thing here. There's no female term. But if we take the derivative of beta 2 female, then we've got this female term. So derivative of that's going to be beta 2. Okay, so that's why normally, if we don't have some sort of interaction, that's why normally the coefficient is what we say is the effect of this variable on the outcome. Okay, but we're going to keep going here because remember we have this interaction. So what's the derivative of beta 3 times children with respect to female? Again, that's nothing. What's the effect of beta 4 times female times children? Now we got female in this one. So the derivative of this with respect to female is going to be beta 4 times children. Okay. In other words, it's going to be this bit right here. Okay. So in other words, what we're saying is the effect of being female on wages varies based on the number of children that you have. Okay, right? And I talk a little bit about how to do that in Stata, but we're not going to worry about that for the exam because we're not going to use Stata for the exam. Okay, we do the same thing for if we had a polynomial. Okay, so remember this is we're just going to take the derivative of this with respect to education. So we're going to do that. So let's take derivative of beta 0 with respect to education. It's nothing. What's the derivative of beta 1 times education with respect to education? It's just beta 1. And what about with education squared? Well, that's going to be beta 2 times education. And then we're going to bring this 2 down and subtract 1 from that 2. So we're going to say 2 beta 2 education. And that's where this comes from. Okay. So in other words, what we're saying here is that the effect of education on wages depends on the amount of education. Okay. All right. So what I have in this review bit here is a formula sheet. I'd advise you to print this out and not have this on your screen, mainly because you kind of want to have it at your fingertips. Okay, you want to be you don't want to have to go back and forth. Same thing with this t distribution table that I've got back here. You want to have this at your fingertips. Okay. So that's going to be it for really all the stuff that needs to be on the exam. So I did basically an overall kind of skim through a lot of this stuff to make sure you knew kind of what's on it. So when we have our Zoom meeting tomorrow, then my expectation is please listen to this first and then come here for some more, for the Zoom meeting for more in-depth discussion and let me know exactly what you want to talk about, and I'll stay for the entire class period. And you can also, again, come to my office hours. I don't get nearly enough people coming to those office hours, so you must feel extra comfortable, or you may have something else to do during that time. But again, if you have something else to do during that time, then set up an appointment with me. So I try to be fairly accessible. So if you're having trouble with any of this material, just talk to me about it. All right.